Okay, today I'm really excited to talk to you about rate laws. So we're talking about chemical kinetics, which are kind of the rates of chemical processes, and what are the different factors that go into that, and how do we describe them. So I want to talk about one way that we describe this, which is a rate law, which is just an equation that relates the concentrations of my reactants and a catalyst, if there's one involved, to the rate of how quickly they occur, because the amount of each of my reactants and a potential catalyst are going to impact that the speed of that particular process. So if we have a generalized expression that looks like this, so we have kind of these lowercase letters are my coefficients, these molar quantities that balance out this chemical reaction. And then my uppercase letters are my chemical species, and let's call C here my catalyst. And remember that a catalyst is a chemical substance that speeds up a chemical process but is not itself used in the process. So C is my catalyst here, if there is one in the process. Let's say there is. So my rate law, which is my expression here, says that the rate is going to be equal to some constant K, and that's going to be different for different chemical reactions, times the concentration of my first reactant raised to some sort of power, which we'll just call M right now, times the concentration of my species B, whatever that reactant is, raised to some sort of power, times the concentration of my catalyst raised to some sort of power. So recall that these brackets here, these kind of square brackets, indicate concentration, and concentration is usually in molarity. And then these exponents, kind of my M, N, and P, are all experimentally determined powers that we raise these to. And the greater the power, the more of an impact that has on the speed of the process. We'll just call those that they're exponents that are determined in the lab. So we have to either be given information about them or we have to find them ourselves. So when I tweak these concentrations, how much of an impact does that have on the rate? And this constant, of course, too, will have an impact on the rate. So this is kind of our rate law expression. This is the generalized way that we can write out a rate law. Now note that we're not taking into account our products, we're just taking into account the concentration of our reactants, and if there's a catalyst present, then that's what we're going to use. Okay, so let's kind of take a real life situation, then that's kind of my generalized. Let's take a real life situation and talk about what that looks like. So if I have a rate of, and it doesn't even matter what the reaction is, there's a nitrogen dioxide and fluorine as reactants. So what this says is if there's no exponent there, then we can think about that as, a 1, right? So if we are putting the exponent in there, then we would say that this is first order with respect to my NO2. Okay, which means that there's this first order dependence on the concentration of the NO2 to the rate. Okay. We'd say it's also first order with respect to the fluorine, because of the exponent here. So the exponent tells me the order of the reaction, and this is going to be important, and we'll talk about orders of reactions and integrated rate laws and all sorts of things in future videos, but for right now we're just introducing this idea of a rate law. There's a constant that's related to this equation. There's these concentrations of my reactants. They're raised to some powers. And then we have this kind of, this way that we can express how much that concentration is going to impact the rate. Okay, so when I'm looking at these guys then, I have first order with respect to NO2, first order with respect to fluorine, and we would say the overall rate order is second order. It's a second order reaction, and it's second order because I have dependence on two things, and those two things are both first order, so I add together the order of my individual kind of dependence there to give me the overall rate order. Now I can also have a zero order dependence on a substance, meaning that it doesn't matter how much there is, right? That's not going to impact the rate, or if I double the thing, then it's just going to have It's just going to double the rate. It's not going to have any direct impact on the rate at all. So it's not going to be a factor at all. So we have something like this, and we would express it like this in the overall. So maybe I did some experimental determination here, and I figured this out, and I have a zero order dependence here. So let's say that I have second order dependence with respect to my NO2 in this case. Again, different reaction. And then a zero order, and I'll just kind of slash my zero so it doesn't look like an oxygen. It kind of looks like a Q here, but that's a zero with respect to my carbon monoxide. Okay, so what that means is that there's no dependence on the rate of the concentration here. So if I increase this, it's not going to mess with my rate at all. It's just going to go up in the normal way that it would, kind of depending on whatever all else is going on in the reaction. It doesn't matter if I tweak that concentration. So we would actually probably not even include that, right? Because anything to the zero power is 1. And so if I have a 1 here, then I could just rewrite this as the rate is equal to the constant times the concentration of my NO2 here squared. So we'd probably rewrite it that way. It's not wrong to include the zero order dependence, and it actually gives you some information about things depending on the experiment that you're doing in the context, but this just kind of cleans it up a little bit. And we would say that this is also a second order reaction because it's a second order dependence with respect to the nitrogen dioxide here. Okay? All right, so that's a little bit about the notation. Now let's see if we can write a rate law given some data, some experimental data. So if I go into the lab and I do this reaction, so I'm doing 2 of my nitrogen dioxides to give me 2 nitrogen monoxides and 1 oxygen. Then if I do this process and I do it twice, the first time I have this concentration, 0.01 molarity of my nitrogen dioxide, and it gives me this rate. And again, my rate is in concentration per unit time, so molarity per second. And then if I double it, then this is what happens to my rate. So we can figure out then the exponents based on experimental data. So we know that our rate is going to look something like this. The rate is equal to some sort of constant times the concentration of my reactants raised to some sort of power. Okay? This is the generalized expression for this particular equation. You'll always be able to write a generalized expression because right now I don't know what that exponent is, but given these data, I will know what the exponent is. So when I'm looking at this here, this is kind of my expression. And then what happens when I'm going from one trial to another is when I double this concentration, then what happens to this rate? That's kind of what I like to do when I'm solving these types of problems. So when I double this, what happens to this guy? And hopefully you can see, or if you can't, then you can plug it into a calculator. This one is 4 times larger than this one is. So when I doubled this, this guy went up by a factor of 4. Okay? So if we're thinking about this in terms of the ratios, if I have kind of some sort of rate that's associated, here's rate 1, and here's rate 2. That if I'm thinking about these expressions and I said, well, I doubled this guy, when I doubled this guy, this one went up by 4, then if I think about these as a ratio, so I'm going to take the ratio of rate 2 to rate 1, and the only thing that I've changed then is doubled this guy. So I had 2 times the concentration of my NO2 raised to some sort of power over the concentration of NO2 raised to some sort of power. So if I am looking at this expression here, then I can simplify this expression by getting rid of my concentrations. Right, so this is 2 to the m times NO2 to the m, so I can get rid of my NO2 to the m's, and then that leaves me with 2 to the m. Okay, so the ratio of my rates gives me 2 to that exponent, and then 2 to that exponent equals this ratio of my rates that I calculated in the lab, or that someone calculated in the lab. Someone found out the rates in the lab, and then this is what they did to solve for it. molarity per second, which we said is 4. So essentially my 2 to the m is equal to 4. So to what power can I raise 2 to in order to get it to 4? Well, m must equal 2. Okay, so when I plug this back in, then I'd say, well, my rate law expression is that the rate is going to be equal to some constant k, and I could actually go in and solve for k as well, because I have these different data sets, times my concentration of my NO2 squared. So I'd say that there's a second order dependence on my nitrogen dioxide here. And again, if I wanted to, I could calculate this k because I have the rate, and I could calculate, so plug in my rate here, I have my concentration, plug in my concentration there, solve for k. And I should have the same k value for both runs. So I would try it for both, because that will tell you if you have the right rate law expression for these kinds of things. Okay, so second order reaction there. Let's look at another one where we do 3 trials and we have a few more things going on. So without actual numbers, I kind of like working with variables because I think that kind of shows what we're doing and what's going on. So if I have this reaction here, so I have 2 of my nitrogen monoxides, 2 of my hydrogens giving me nitrogen, and 2 waters. Everybody's in the gas phase. Then the expression for my rate is going to be that the rate is equal to some constant k times the concentration of my nitrogen monoxide raised to some power times the concentration of my hydrogen raised to another power. Again, I don't have a catalyst, so I'm just focusing on the concentrations of my reactants. All right, so now I need to solve for m and n, so I need to look at these guys and say, well, how are they changing? What information am I given from these experimental data? Well, if I just, and x could be anything, but if I look at this and I said, well, I doubled my concentration here, what happened to my rate? Well, you can see that it doubled. When I doubled the concentration of my hydrogen, this guy doubled as well. And if I'm looking at my nitrogen monoxide, then I also want to compare where did I double but keep the other one the same. I can't go from here to here because this one doubled, that's true, but this one halved, so then I'd be looking at the dependence on 2 different variables. So it would be easier to compare the first to the third trial, right? So I doubled this one, but this one stayed the same. So this guy doubled. That's the only thing I changed going from run 1 to run 3. So what happened to my rate in that time? Well, it went up by 4 times. That's not 4. That's 8 times. It's like, wait a second, doing the math. So if I do my 0.048 divided by 0.006, then that's 8 times as much, right? There we go. Simple math. That's where they get you. Okay, so what I'm looking at here is if this is my m value, then I'm focusing on this one, going from 1 to 3. So comparing 1 to 3, then that gives me 2 to the m is equal to 8, right? So I doubled this guy. This changed by 8. So just like the calculation before, if we take the ratio of these guys, then that gives me 2 to my variable that I'm looking for. And so 2 to what power gives me 8? Well, m is equal to 3 then. And then I can do the same thing for these runs. So this one I'm going to compare 1 to 2. So I doubled my concentration of hydrogen. My nitrogen monoxide stayed the same. And when I did that, I doubled it. So that would be 2 to the n. So now I'm looking at this variable here because it's related to my hydrogen. 2 to the n is equal to 2. So 2 raised to what power is 2? Then n is going to be equal to 1. So when I rewrite my expression with my actual exponents in there, I would say that the rate is equal to some constant k times my concentration of nitrogen monoxide cubed times my concentration of my hydrogen raised to the first power. And you can either put the first power in there or you can just leave it blank because that's implied then that it's the 1. And again, you can solve for k because for each of these runs you have the rate, you can plug that in, you have the concentrations. In this case we have variables, but if you had actual concentrations you could plug that in and solve for k. Alright, so that's rate laws.